Hello everyone and welcome to a new discussion which we are going to have, artificial recharge techniques and designs. And before we enter in this discussion, I would like to mention here that now we have reached to end of this course, and this is the last presentation or last discussion on one important topic, which is groundwater engineering. So, I very much hope that you must have enjoyed so far, and let us begin this new discussion. As we know that there are several techniques and designs are coming, and there are many innovations are also being done in case of artificial recharge techniques. So, we will be looking these techniques in various ways, or these techniques can be divided into various categories. So, first category of or first class in this one is direct technology and indirect technology. So, we would be mainly focusing on direct technology and mainly also on the surface methods which are there. So, in under direct technology there are three categories: surface, subsurface and combination of both surface and surface. So, our focus in this discussion is going to be only mainly surface technology for groundwater, artificial recharge of groundwater. Now, there are lot of systems or lot of innovations are being done to use this surface water, even the rooftop water harvesting, so that the water, whatever the water, rainwater in monsoon time, whatever is available, maximum if we can put in our aquifers, and that can be the best solution to solve our water issues. So, the first the first technique under this direct surface method is, or surface technique, is the flooding or water spreading. So, like here what you see in this photograph, this is the real picture, a field photograph, which is mostly very simple and most widely used method, which is the flooding, the water spreading. Now, here the important investigations which will be required, we have already discussed in previous discussions, but just very briefly, that the area which is being chosen for flooding or water spreading method, and that the top soil should not be clayey soil, it should be sandy soil and so on. And secondly, that the rocks underneath which are there should not be impervious in character. So, if even in hard rock terrain it is being done, then the top part at least it should be highly weathered and fractured, then only the real benefits of such a method or techniques will come. Further very important thing which is now being done when we are going for flooding and water spreading, that because of high evaporation losses, that component we have also discussed in previous or before that in our discussions. So, how to minimize the these evaporation losses. So, a new approach has been is coming in a large way now in India, in various parts of India, that floating solar panels are being put. So, that reservoir or that flooding water is being used for two purposes. Basically, it is being used for recharge, and this area which is going for this, I would say for the area which is being invested for artificial recharge, the same area is also being used for solar energy, and this is really becoming very important. There are various sites, I will give you just one example, Omkareshwar on near the Narmada or of Narmada bank, and whatever the backwater which they are having, that area is becoming a very rich from solar energy point of view. So, you are exploiting for solar energy, and the same time you are reducing the evaporation. So, these the combination of these two can be very beneficial for those areas where the temperatures are generally high. And this water which is we are storing in flooding or through water spreading is the directly transfer into an aquifer without infiltration. So, that kind of facility can also be developed, that this can be directly transferred to the aquifers, and if it is a recharge site for a confined aquifer, it is wonderful. For that again you require initial investigations, all kinds of investigations, so that we will make sure that where these spreading structures are being created, those structures are located in the already recharge areas of a confined aquifer. Even if they are not there, we can also go for unconfined aquifer condition. So, in such structures where these have been chosen, water percolates naturally through the unsaturated zone of soil and soil profile and join the groundwater table. So, very direct method of artificial recharge. This is another way of creating depending on the slope and other soil conditions, and from management point of view also, that instead of a large water spread area, you can one can create small portions within that area. So, this is basically such structures or such approaches are mainly suitable for flat terrain or flat topography, for example, in Indo-Gangetic alluvial plain. In earlier discussion, we have seen that many red areas in terms of groundwater depletion are being seen in this Indo-Gangetic plain. So, Indo-Gangetic plain is also required now a lot of groundwater recharge structures. So, in this in such places, the water is spread as a thin sheet, and then higher rates of vertical infiltration is obtained. In earlier times, what farmers were doing, after this crop before the monsoon, the bundings which were there in each farm, and that bunding was stopping water or reducing the surface runoff for some time, delaying the surface runoff, and that was also very good approach for groundwater recharge. And there are many people or many organizations in India, especially I am talking in hard rock terrain, where they are promoting this bunding of agricultural fields, and they are saying it is not an innovative thing. In the past it was being done, and people if they go for a larger agriculture area, then problems are there. So, smaller agriculture area or farms can be benefited by such bunding also. So, this is nothing but a kind of bunding. You are spreading a thin film of water and doing that thing. If the area is not flat, if there are some slopes are there, gentle or whatever, so or you are having a irregular topography, which is a shallow flat bottom and closely spaced ditches or furrows can provide maximum water contact. So, here what we are seeing, that ditches have been created here, and then also you are having ditches, cutlets is there, supply ditches are there, and series cascading ditches are there all along the slope. So, whatever the runoff which we can delay or stop, it is being, or whatever the surface water flow or runoff can be captured through ditches, and we will allow the water to recharge our groundwater regime. And excess amount can directly go, of course, to either to collecting ditch or can go to the stream which might be there in the nearby place. So, for flat terrain solutions are there, for irregular topography, shallow flat bottom areas, again solutions are there. So, such kind of ditch and furrow method requires less earthwork and is less sensitive to silting, because the ditch number 1 will have the maximum and second, and you do not require too much land also for this kind of work. So, in the remaining area, the other agriculture practice or forest and other things can go on, that those kind of activities, and still you can recharge the groundwater regime. And this is a very common practice being followed in Himalayan terrain, in many parts of Himalaya also. Now, generally there are 3 patterns of ditches and furrows systems are adopted. First one is the lateral ditch pattern, second one is the dendritic pattern, and third one is the contour pattern. Generally these the patterns are based on basically the topography. So, first we will look the lateral ditch pattern. As you can see in the figure, that you are having here a outlet channel, and these are the lateral ditch which you are having, and then you are collecting water, and then it is going there. and direction of farming operations can be in this direction or this direction. So, you can say the slope either in this direction or so. This is of course a view is tilted, not really shown as a flat. So, the water from stream is diverted to the feeder channel as you are seeing, or outlet channel, and from the ditch, which is smaller ditches are made at right angles, as you can see that these are the smaller ditches which have been made at right angle. And the rate of flow of water from these feeder canal to these ditches is controlled by gate valves. So, gate valves, some it will require some extra efforts, some extra expenditure, but again it will depend on type of terrain which you are having. Another type of approach for ditches is lateral. So, in lateral ditches furrow depth is kept according to the topography and also with the aim that maximum wetted surface is available, because more wetted surface, possibility of more infiltration or percolation, and infiltration and then percolation. So, a uniform velocity can also be maintained if we are having more wetted surface, and also lateral ditch pattern. Second is whatever the excess water is which is routed to main stream through a return canal along with residual silt. See, in this many such cases the problem will come about the silt. So, the approach is that you have all constructed all this, now the silting is there. So, after each monsoon the silting, or before the monsoon, the desilting can be done of these ditches. So, that when next monsoon comes, it will have a full access to the channel. Third type of third type of pattern which is used for ditches is dendritic. As you know that in natural drainage system is also dendritic, which is something like a tree kind of, or branches of tree. So, in this the stream water is diverted from main channel or main canal to series of small ditches spread a dendritic pattern. So, here you are creating a kind of distributory channels from the main channel or main canal, and then this bifurcation of ditches continues until practically all the water is infiltrated in the ground. So, you keep that kind of thing, so that the water is spread throughout the land which is available through this dendritic pattern or pattern of ditches which is created. Fourth types is contour pattern or contour bunding. Contour bunding is very common in Himalayan terrain, very common, because generally slopes are high. So, this works very well. One more important thing I can share here, that like in Himalaya, or if you see in Garhwal Himalaya or many parts of Kumaon Mela, large the outward migration of people has happened at a large scale, and hundreds of villages in these regions of Uttarakhand have become almost ghost villages. There are no people left, or in villages if there are people left, then they are either old people, ladies, or kids are there. So, what is happening, the agricultural practices which were going on have completely stopped there, and the agricultural fields, those were the terrace farming, all have been abandoned by that. So, the result of this, that the springs which are in downstream are also drying up, because whatever the rainwater which is coming and encountering a hard surface, earlier they used to have a plowed surface and agriculture was there. So, they were the interference by all this. Now, that interference by vegetation has gone, intervention, and what is happening when rain comes, all the water flows as a surface runoff and no water stays. So, if we are, and these bundings which they used to have for each agriculture field on one side towards the downslope side, that is also getting broken because it is not being maintained. So, result of this, that groundwater regime in those areas are not getting recharged and the springs are getting dry, and then it is further forcing people to go for migration to the places where they get the water. So, it is a kind of self inflicting things which is happening, and this can be controlled First of all, these bunding has to be maintained in these areas, one, and secondly, if nobody is ready to do any agriculture practice there, then just before the monsoon each farm should be ploughed and left there. So, if that is there, then some vegetation will grow, that will put some resistance, bunding is there, the rainwater will stay for some time and that will recharge the groundwater regime. So, infiltration will take place as not happening nowadays, and in past it was happening. So, we know what are the problems. The only thing is the solutions are not being done on the ground. As we can see here, these are the bunds or trenches. So, if it is slopy ground, then this part is get like this. Similarly here. So, it is a series of, sometimes on a particular slope you can count even 100 farms just in form of terrace farming, and no water is staying there, whatever is coming is just going down in the stream. So, ditches in such a, for contour pattern or contour bunding, ditches are excavated following the ground surface contour of the area. That means, if you measure the level along the ditch, you would find that it is horizontal. So, when the ditch comes closer to the stream, a switchback is made, and thus the ditch is made to meander back and forth repeatedly. So, this kind of switchback can be done, and then this bunding goes back. So, at a lowest point downstream, the ditch joins the main stream, thus the returning the excess water to it, and this is what is happening in all these hilly terrains of Himalaya. This is the example here. See, if bunding are there, bunding are being maintained, there are some plants are also there, and farms have been ploughed, it will really recharge the groundwater. The fallow land is very useful from groundwater recharge point of view. So, it's the surface should not become hard. If agriculture practice is not going on, then surface will become hard in few years time, and that is very bad from groundwater recharge point of view. In case of contour bunding, and which is a part of a good practice of watershed management also, to build, and this also stops the soil erosion, that is another important thing. So, the soil moisture will be retained, it will stop the soil erosion, it will recharge the groundwater regime, and springs will have water all the time. And this bunding, basically the name has come from the construction bunds along contours of equal land elevation. So, the knowledge was existing there with the villagers. So, in this technique generally adopted at a low rainfall areas, maybe less than 800 meter, but this can be, I have seen in places where more than 800 or 1000 millimeter rainfall is there, but still bunding is there. And in gently sloping lands, for long slope lengths are available and the soils are permeable. So, some these conditions have to be fulfilled, and where earlier the agriculture was going on, that means all these conditions were being fulfilled, and therefore, these areas were very successful from agriculture point of view. So, however, if you are having other problems like poor internal drainage or clayey soils, then these areas are not recommended for bunding. Further, that contour bunding involves construction of narrow based trapezoid embankments or bunds, as you can see here, and along contours to impound water behind them, which infiltrates into the soil and ultimately augment groundwater recharge. And such type of bunding structures are feasible in hilly areas. I gave the example of Himachal Pradesh, Uttarakhand, Sikkim, northeastern states, many places, and even they are having the paddy crops, and they used to have a very different variety of paddy which we do not get in plain areas, and very healthy from health point of view, where those varieties were very nice. So, now we will see that what are the site characteristics and design guidelines for such kind of approach, that is contour bunding. So, this method is adaptable to irregular terrain. The water contact area seldom exceeds 10% of the total recharge area. Ditches should have slope to maintain flow velocity and minimum deposition of sediments, and ditches should be shallow, flat bottomed and closely spaced. Why flat bottom? So that we are trying to provide the maximum area for groundwater recharge or for infiltration, and closely spread to obtain maximum water contact area as much as can be made. That will help. And the width depending on the area, slope and other things, but generally width can be of 0.3 meter to 1.8 meter in dimensions. Also in the depth also, so here it is basically the depth means roughly 1 feet. You can have 1.8 meter in the width, and the length you as much as you want. Collecting ditch to convey the excess water back to the mainstream channel should be provided. Otherwise, what would happen if a the lot of rain occurs, then it will harm the bunding, and nobody would like to put again efforts to maintain or redo the bunding. So, the main that the excess water it should be made in a manner that excess water goes to the main stream which is in down play. Now, we are having now the second approach for which is which comes under direct surface groundwater recharge or artificial recharge technique, and which is called the basing or percolation tanks. Or when we talk about large area, then we can say basins, or if we are talking about small area, then percolations. Simple approach, you just require a percolation tank. So, you allow water to stay there as long as water is there. There will be some losses as in form of transport evaporation, does not matter, but the large amount of water or large volume of water will infiltrate and then finally percolate and may join the groundwater table. So, the percolation tank can be defined as an artificially created surface water body. In old time or still in almost in every village town, we are having we say talab or tank and other words. Many of these were constructed, they were not natural, these were constructed for groundwater recharge. That means that in our older time people knew about these techniques, nothing new, no innovations yet about these things. But what happened in recent past that many such tanks which were very large or small, encroached by the people, or silting has taken place, and therefore, the volume of water which used to store has reduced very significantly. So, they have in fact they have become ineffective, and further at the bottom the silting or the clay materials have deposited. So, even if you are having water that is not going down, and whereas it is going as a great loss in form of evaporation. So, that is why the redoing or in the before monsoon in summer time at many places this is being done, that these old tanks or old talabs, ponds are being maintained now. So, the bottom part, the clayey soils or clayey material, silty material is being taken out, dredging is taking place, so that in the next monsoon or in the monsoon coming there will be more recharge from this. So, percolation tanks, as we were saying defining, can be defined as artificially created surface water body in a highly permeable land submerged area, so that the surface runoff is made to percolate and recharge the groundwater storage. So, aim here is to capture the surface runoff, but the same time some investigation or lot of investigation will require to find out the most suitable land which is having highly permeable land surface. If it is there, then only. So, that means the top soil should not be clay soils, and if it is hard rock terrain, then the top part should be fractured, weathered, then only these would be successful one. And after before every monsoon, the clay which has settled or or fine material, fine sediment which have settled at the bottom should be cleaned, should be cleared, and then these will perform very well from groundwater recharge point of view. This is a simple satellite image which you can see that lot of such tanks have been created, and of course, if such things are done, then definitely it will recharge the groundwater regime. Within a year or two, you will start seeing very positive results from these efforts. So, percolation tanks are not provided with the sluice or outlets, means whatever is the water is coming, it should stay there. If it is overflow, it will spread in the adjoining areas or adjacent agricultural fields. So, there is no extra efforts or construction is required, just you allow water to stay for longer time rather than or capture the surface runoff. And so that these outlets are not for discharging water from the tank for irrigation or other purposes. There is no desilting, there is nothing, just simple dug out of a few meter of the earth and put on the side, but in the manner so that the surrounding water can enter into the tank and stay there for some time. However, these there might be problems about spilling of surplus water, and that may enter to other places and can create some problem. So, what is meaning here is that everywhere such tanks should not be created, only with the consensus of people and locating a suitable site. Suitable site means if it is not a really agricultural field or a abundant place, something like this, as you can see here, a simple tank, a water tank has been created, and that is does not require much maintenance. Water from upslopes is coming here, staying for some time and going downward first, some losses as in a form of evaporation, and if it is overflow, some outlet will be there through a sluice or gate, and that will come out. So, this is the most prevalent structure in India, as this one you are seeing. It is used to measure the recharge the groundwater reservoir by highly permeable land areas. I am saying even the highly permeable land areas are not there, but water is required. So, wherever it is possible, such tanks should be created, and no matter whether they will to some extent anyway they will recharge the groundwater regime. The rocks are not completely impervious on surface, because they are fractured, they are weathered, and they will provide some recharge to our groundwater regime. So, efficacy and feasibility of the structure is in hard rock terrain formation, where rocks are highly fractured and weathered. So, there it will also work there. If we see in form of cross section, and then a percolation tank is here, but some bunding or something with local material or some other things can be done. In our earlier discussions related with groundwater recharge, I showed examples of using Bundelkhand granite, in Bundelkhand granite using quartz reefs as a band as a dam access, and then in the upstream you are blocking this and you are holding water for some time. Similarly, in a state of Maharashtra, Andhra Pradesh, Madhya Pradesh, Karnataka, Gujarat, Uttar Pradesh, many places such things are being happening, and like the positive news which we have been getting from Gujarat and Telangana, I am sure if sincere efforts are made in these states also where water is a problem, then in few years time we will be start listening very positive news because of all these efforts through artificial recharge. So, in Karnataka the percolation tanks have been constructed in plenty, even in the basaltic lava flows and crystalline rocks. So, you are having hard rocks or igneous rocks which are having only on surface, but whatever the water which is going as a waste, if we can hold for some time, I am sure it will recharge our groundwater regime. Another example of percolation tanks are feasible in mountain fronts occupied by talus scree deposits. So, in all kinds of places, all kinds of geologic formations, these can be constructed. In hilly terrain also these are being done quite good. It is a part of, if that part is available, it is a part of good practices of watershed management. So, these tanks can also be very effective, are being found effective in Satpura mountain front in Madhya Pradesh and Maharashtra area, Bhabbar zones along the foothills of Himalaya. These are also very useful to recharge the groundwater regime. These percolation tanks with the wells and shaft, like here it is shown. So, at the bottom you are having wells, and along this you can also have a shaft here. So, all around you are trying to puncture the top rock which is having a low permeability material. You are through these wells and shaft you are forcing water or compelling water to go to the permeable material, and that is a confining aquifer. So, you may be getting the water something like that, and also the effect of that the recharge is also shown in a form of you can say reverse drawdown. So, as you can see here that this is very further effective. Simple tank may not be as that effective as having at the bottom of the tank few wells, few bore wells without any pump or anything, just left there just to recharge the groundwater regime. So, these are also very good, especially in those areas where you do not have the top surface, do not have much weathering or fracturing, but you know at certain depth that after geophysical investigations, if that knowledge is there that at certain depth these we are having a confined aquifer conditions, then at the bottom of these tanks such wells can be created. And this is what it is shown here, that percolation tanks with wells and shaft are also constructed to recharge deeper aquifers where shallow or superficial formations are highly impermeable or clay with the certain modifications. So, depending on the conditions, slopes, geologic formations, soils and availability of water, all kinds of innovations at local level can be done, which are most appropriate for that part of the land. So, detailed analysis of course will require, as I have said, about rainfall pattern, number of rainy days, dry spells, evaporation rate, detailed hydrogeological studies, demarcated suitable pattern. For a small scale, if you do not have any information, still these percolation tanks will recharge the groundwater regime. But for a very effective, efficient percolation tanks of large size to recharge a large groundwater aquifers, for which definitely you require, because that will require a lot of investment compared to a very local level percolation tank. So, in Peninsula India, large part of India where we are having semi-arid climate conditions, and at the same time we are having storage capacity of pollutant can be designed such that the water percolates to the ground water reservoir by January before the temperature starts rising. So, that the evaporation losses would be so there will not be in these months, there will not be much evaporation losses and before the temperature rise, because once the months or the season becomes little warmer, there will be more loss too. So, that the design of these percolation tanks can be in a manner that whatever the water which has been collected during rainy season goes down in subsurface reservoirs, and there will not be evaporation losses. Even if you are having excess water, even if you can store on surface for longer time, another approach which I have just discussed to have floating solar panels. Further this about the percolation tank can be normally constructed on second or third order stream also. So, it is need not to go only for first order and in a catchments for second order or third order, but one should not go for first order because the catchment area for first order is going to be very small. So, best would be if possible go for third order or fourth order streams, not to the the main stream, so that a lot of water can be sufficient amount of water can be collected and we will allow the percolation to go. So, in this artificial recharge structures, when we choose the percolation tank, then there are some requirements about investigations that we need to have hydrogeological investigations where the percolation tank is being planted, or the which rocks which are coming under the submergence area should also be checked from permeability point of view. I would like to say here that all the time one may not be having a highly permeous or permeable rocks at the surface. So, even there is some permeability to some extent does not matter, still such tanks can be constructed and the efficacy may not be of that great, but whatever the water which is being wasted will be stored for some time and definitely it will recharge the groundwater regime to some extent. So, there is no harm if the construction cost is not much. Third important thing is that the weathering of rocks, as one should expect that it should be uniform, but we know that the rocks surfaces topography is not uniform, homogeneous and infinite in character. So, but where these tanks are being created, if it is possible that we can have a uniform weathering and fracturing of rocks, then those areas are also good. Now, these ultimate purpose of this percolation tank to conserve the surface runoff or catch the surface runoff, capture that water and divert the maximum possible surface water to groundwater. And so, the effort should be in a manner that there are less losses in a form of evaporation, and that I was mentioning earlier also, that if large percolation tanks are being constructed, then top part can also be used to reduce evaporation from surface of water by having floating solar panels. The water which has been accumulated in these tanks after the monsoon should percolate at the earliest, so that before we lose the much water in form of evaporation, because then summer months would be approaching. So, January, February for some areas are good. By that time, if water can go underground, that would be wonderful. But if it is not, and if the large tanks are there, no problem, these floating solar panels can be installed there. So, one will have energy also available to villagers. Now, this submerged area which will come under this percolation tank should also be in uncultivated land as far as possible. This is always, if one suppose some government agency find that other things are suitable except that area is cultivable land, then people will be reluctant to give that land for percolation tank. So, I would suggest that initially though that part of the land in a area or basin or watershed should be such where no agricultural practice is taking place. And further percolation tanks should be located on highly fractured weather rocks for highly or speedy recharge. If these percolation tanks are being constructed in alluvium or where are you having boulder formation, then such areas should be preferable if that choice is available in some area. Alluvium you can find, or alluvial fill valleys you can find in along the rivers or streams or rivulets which are there. So, those areas are quite good from recharge point of view. So, the aquifer which we are trying to recharge should have sufficient thickness of permeable vadose zone to accommodate recharge. If it is already fully saturated, then there is no use. But if there are fluctuation pre-monsoon, post-monsoon, then still those regimes or those aquifers can be recharged. The benefited area, we have seen this submerged area versus benefited area ratio and other things. So, that is the area which is going to be recharged. The benefit area should have sufficient number of wells and cultivable land to develop the recharge system. So, that whatever the benefits are being created because of groundwater recharge should be used locally, because otherwise there will be some problems. Water in subsurface condition may go elsewhere, and directly people, those who have invested their land, will not have the advantages. Further, detailed hydrogeological studies are also required, which will encompass the surface runoff assessment and design capacity which affects and should normally be more than 50% of total quantum of rainfall in catchment. So, these designs should be made in that manner. Now, overflow, spillway, waste piers, sluice, gates, all kinds of these suitably designed to allow flow of surplus water. Otherwise, what would happen? It may harm the bund of these tanks, and for next year then, or for even that year, lot of water, valuable resource in form of water, rainwater will go away. So, there is always a need for a spillway or waste weir or that kind of thing which will allow go from away, so that we can have the maximum capacity and we can fill also up to the maximum level. There can be also cut-off trenches be provided to minimize seepage losses both below and above the nala bed. And to avoid erosion of embankment, that is a big concern. As I have said that not only the siltation happens, not only the encroachment happens, but sometimes the erosion of bank also creates problem. Especially I have seen in the field many newly constructed percolation tanks are having this problem of erosion of embankments or bunds. And so, due to the ripple action, stone pinching provided should be provided in the upstream up to high flood level. If it is depth is done, then this erosion of banks can be avoided, and that is done for large structures. But if it is small structure, then may not be required, because otherwise it will involve lot of cost also. Further, the benefits, how much benefit it is being provided, that should also be monitored, so that the neighboring villages, neighboring people or people in other parts of India can be convinced that these are very good. So, the monitoring mechanism in benefited area as well as catchment area using observation well, staff gauges to provided to assess the impact and benefits of percolation tank. This is very, very important. If any such structure for artificial recharge has been constructed, then decision makers would also like to know before they approve another recharge structures in nearby places, what are the benefits which the earlier construction or earlier percolation tank has provided, and that can come only. Now, the one other important point which we are discussing here is stream augmentation, that how a stream recharge structures along a stream will augment water in the stream ultimately, and these can be cascading as also shown here, that one after another. So, tail of one water storage structure or a small dam, check dam ends, another after some time or after some distance another structure can come, and we can have a series of such structures even up to the second order of streams. So, we can do the rainwater harvesting through check dams, very popular method. After these tanks and spreading method, cement plugs and nala bunds are there. And even we can have, instead of cement plugs, we can have a purely local material available there with some cement, and that will stay for longer time. Only on yearly basis before monsoon, these have to be checked and should maintain. If there is some damage because of previous monsoon rain, that should be repaired, and these will work very well. And if there is a silting has taken place, that should also be removed. So, check dams, as name implies, that they are checking basically the runoff which is or a stream flow. And so, check dams are constructed across small streams having gentle slope. Now, this is very important, across small streams on large streams check dams are not constructed, and if you want to construct a really large reservoir, it will cost lot of time and lot of energy, and gestation time is also very high, and it will inundate large part of the land. That is not a good approach from groundwater recharge point of view. If that reservoir is multi-purpose for hydropower, for lift irrigation, canal irrigation and other things, then those options can be explored. But just for groundwater recharge, those options are not there, should not be explored at all. The main is the these check dams across small streams. This is the emphasis I would like to bring here. Small, only along small stream, because you will not have much water to store, and secondly the simple structures will work, will stay to all these seasons, monsoon season. And once you are having slope which is less, also then these will be there for long time. This is how the design can take place. So, side elevation is something like this, the cross section can be like this. So, you are having a foundation which goes little deeper, just 0.6 meter, roughly 2 feet, and you fill with the large boulders here, and then you are having stone pitches and bund like this, of having just a height of 1.2 or 3 meter depending on the location conditions. And on the side elevation you can have the this kind of thing, again 0.6 for the bottom part or below the surface part, and a 1:2 or 1.2 or 1:2 slope like this you can have on the side using the local material or big boulders of the rocks. So, site selected should have sufficient thickness of permeable bed or weathered formation to facilitate recharge of stored water within short span of time. That kind of investigations is required anyway, but just looking any site in hilly terrain like this or gentle sloping terrain like this, one can get very good idea without much instrument based investigation that what kind of recharge it will provide. A real structure is also shown here. You can see the side walls and you can see the main check dam section of main check dam here. So, this is storing a not large water, the pressure of water and other things will not be there. If there is excess water, it will come out from this check dam and flow downstream, no issue. So, initial water will definitely will get settled here and more rain occurs, overflow is provided. So, water is stored in such check dams or these nala ones structures is mostly confined to stream course and height is normally less than 2 meter. So, if you keep that kind of height, not much pressure on structures and structures will stay for these structures will be sustainable for some time. Design based on stream width and axis, and then water is allowed to flow over the wall as I mentioned here, the front wall or check wall. So, in order to avoid scouring from excess run of water, the cushions can be provided at the downstream side. So, that kind of precautions can all be taken, but as suggested earlier that if slopes are less, then such problem will not be there. And these are the mainly confined to stream courses at this height is normally very less than 2 meter, as you also see. The real structures photograph is also there, completely cascading, slowing the stream runoff and same time it is recharging the groundwater regime. So, this way you can harness the maximum runoff in the stream. Series of such check dams, cascading dams can be constructed to have recharge on regional scale. If such gentle slopes are available, lot of water is available, this is the best way. It will also slow down your erosion, and that is another advantage in hilly terrains, because soil erosion is a big problem, valuable resource, soil is a valuable resource. So, that will also can be minimized through these things. So, series of small bunds or weirs are made across selected nala sections as you are seeing in the right figure, and so that the water which will flow is on surface and stream channel is impeded, that will delay the flow, and the water is retained for some time, and with moving the runoff is velocity is slow, and therefore, ultimately it will recharge our groundwater regime. If they are located in highly permeable rocks, and then it is again wonderful. So, this is see that it is a series of dams, not necessarily that these dams should be constructed in one day. See here what you are seeing, and that there is a threshold dam which was constructed in 1978, and then you are having a dam 1 1974, in dam 2 1980, 86, 91, 96, 2003. So, when the first dam was constructed, it was realized that this area can really recharge the groundwater regime. So, the cross section is also shown here, simple design, simple maximum benefits with minimum investment. And once people realize that even this the dam threshold dam which was constructed in 1978 started providing benefits in the downstream area. So, then successively after almost 6 years, 5 years, new dams have started coming. An entire valley has been covered with these structures. So, maximum runoff should be harnessed if possible. Cascading check dams can be constructed to have recharge on a regional scale. These check dams, nala ones, are constructed across bigger nalas of second order streams in areas having gentle slopes. So, as I have said, on very high order streams these should not be constructed, because the water will be too much to handle for these check dams, and these are not a truly very much engineered, but simple engineering solutions are there. So, they cannot have that much, they cannot face that kind of pressure of water. Nalavan, as you know, they acts like a mini percolation tank. The percolation tank is designed to ensure maximum capacity utilization, long life span, cost effectiveness and optimum recharge to groundwater. These percolation tanks in form of recharge. Further, storage capacity, water weir, drainage arrangements and cut-off trench are important features of percolation tank which need proper design. Also, overall design of percolation tank is similar to earthen dam constructed for minor irrigation without canal. And I would suggest that if local material can be used, wonderful. If we want that these structures should remain for longer time, should remain efficacious, then local people or responsibility or ownership to also should be given to the local people. Then these weir or structures will remain for long time and they will of course provide for these things also. So, there are various designs and that because there is a time limit. So, I cannot go for a complete exhaustive discussion on artificial recharge structures. As said in the beginning of this discussion, that lot of innovations, local innovations are being done to capture that surface runoff or rainwater. And there is a lastly I would like to mention here that using these wells or dug wells, abundant dug wells, bore wells, tube wells, recharge structures are being created. Even if there is a bore well, around a bore well, a pit can be constructed and that pit is getting water supply from rooftop. So, rooftop water harvesting can also be done. Before that, a filter can be installed so that whatever the water which is having silt or other materials can be checked by that filter and then filtered water can go directly into the tube well. Because after 1 or 2 rains, the water, the rainwater, monsoon water is really very good in terms of quality. So, directly it can go around a tube well which is having a pit filled with the pebbles and a natural filtering process will take place. Once it percolates downward, finally it will meet the aquifer or confined aquifer or unconfined aquifer conditions. So, that round the year one can have water. So, what I am what I have been discussing here, that there are various possibilities of artificial recharge techniques, conditions based on the local hydrogeological condition, hydrometeorological conditions and area, land area which is available, that is another important thing. So, now with this I would like to end this discussion. Before I say thank you, I am going to complete this complete course here onward and I hope you must have enjoyed. I know that because groundwater engineering itself and various sub branches like modeling, recharge and other things have become individual big subjects. But the purpose of this course was to provide the basics or fundamentals about groundwater engineering, not to go in too much details in terms of latest development or other things, because if we go in that direction then we lose the track of providing fundamentals. So, my focus have been in this course to provide the basics of groundwater engineering, so that one can have a good foundation and then new things can be learned in due course of time. So, with this I would like to say all the best to all participants or those who have come to this last lecture of this course. Thank you very much that you have followed and I hope that you have got some knowledge about groundwater engineering. So, with this I thank you all. Namaste, Jai Hind.